So my talk is the only talk for today that is not about high physics, so you're going to have a small break to observe, and perhaps sit back and enjoy. So I'm going to talk about my field, which is quantum information. I'm not just going to talk about much about the work that we have done, only about the review. Okay? So the title of the talk is Quantum Theory in the Gaussian World. It's about quantum correlations. Let's be out of the talk. So quantum information, I will give a review of what that is and what able to work in this field, because it's a very new field, born in the 90s, and it began more popular, and it's good that you get to know something about that. And next I'm going to talk about entanglement, that I'm sure you all have heard of, and about quantum correlations and why these are important and why people study them. And again, I'm going to talk about a little bit about quantum theory, which is a form of quantum correlation, and it's useful in many stuff. So, some history about the field. In 1982, there was some interest in saying that we can take advantage of quantum theory to signal passing the light and messages. And the famous theorem from the time from Zurich, the so-called no-cloning theorem, said, of course, a big no. And this no-cloning theorem is one of the first results in quantum information. It's very important, and it also has applications in the black hole information paradox. After 3 years, 1985, David Deutsch showed that a computing machine that obeys the quantum mechanical laws, he showed that it can be faster than any classical machine. When I say any classical machine, I don't mean the latest IBM computer. I mean any classical machine that we can imagine, the most technologically advanced that we haven't built yet. So if it's classical, a quantum computing machine that obeys the quantum mechanical laws will be faster. And in order to show this result, he showed that this quantum machine, if it uses parallel, which is basically quantum superposition, so that it does computations at the same time, parallel, and interference, when different states in the superposition interfere with each other, like the two different paths in a double slit experiment interfere with each other. So if we take these two stuff, then we can show this very, very interesting result, which excited very much interest. After 9 years, all these studies in between accumulated to the proof of to show that two enormously important problems were found to be solved efficiently on a quantum machine or on a quantum computer. Efficiently means just fast, okay? For example, find prime factors of an integer. This is a very important problem because our critical system that we use to exchange messages with our phones or on the internet is based on this thing. And it's the following. If I give you two very, very big prime numbers, these are very, very big prime numbers, we can easily do the multiplication. But if I give you the result of the multiplication and tell you to go backwards, finding the two integers, the two primes, this is extraordinarily difficult. So if these two primes are long enough, it will take you into this universe to find them. So basically, this is all our critical systems are based on the fact that we cannot or we don't know how to do this computation fast. And it was shown that a quantum computer can solve this problem in hours, not days. And another problem, this critical problem, which I'm not going to talk about, but it's also very important in cryptography as well. So if these two things are solved by quantum computer, our currently critical systems are of no use. If we build a quantum computer. And these results were shown by Peter Shor in 1994. And in 1995, Benjamin Schumacher, extending the classical information theory of Shannon to the quantum domain, which basically means if we are to communicate with each other, we're no longer exchanging classical things, we're exchanging classical qubits, and many interesting results can follow from it. So after 1995, after all these results, the quantum information field is exploding because of many practical applications. And PhD students started talking out of the Python to these institutions. And so, since then, from 95 onwards, quantum cryptography was developed, which now is not based on the fact that we cannot make a computation like finding prime numbers, but the security of quantum cryptography is based on the physical laws. If quantum mechanics is true, your quantum cryptography is secure. Then, quantum communication. It will communicate by changing quantum systems. Many interesting results have been proved. Counter-theory, for example, super-dense coding. If we use entanglement, we can send two classical bits of information with only sending one quantum bit. And classically, so we can compress the information so much classically it's not possible. And quantum channel superactivation, it's a very interesting word, superactivation. So it means that if you have two quantum channels that are broken, you cannot communicate individually by either of them. If you entangle them and you use them together, they have an error-free transmission. It becomes a perfect channel. Classically, this is impossible. If you have two useless channels, you put them together, that's it. So, also, many of these results that I talked to you about, Peter Shaw, for example, were based on the fact that we have to deal with pure states, ideal systems. But in the laboratory, the states are mixed because there is noise. So we had to figure out how to correct the corrupted information. And quantum corrected codes were developed for this stuff. And schemes for fault-tolerant quantum computation were developed. Fault-tolerant, what does it mean? It means that if the error is below some threshold, then quantum computing can be done. And this was a very important result. And also, relativistic quantum computation was also developed, where in my group in Nottingham, there is a group that works on this, and they're trying to find relativistic aspects like particle creation in the gassing effect, for example, to do useful stuff that we can't do otherwise. For example, this has good influences in quantum metrology. Quantum metrology is something else that popped out from quantum information, and it's basically how to take advantage of quantum effects to very precisely measure stuff, measure quantities. Okay? For example, quantum effects allow us to measure properties more accurately than you can classically measure. And this has potential applications in the measure of the very, very gravitational waves. So this is yet another application. And all these applications that you see here are based on the fact that we exploit quantum correlations. And I'm going to talk about that a little bit later. So what is the word quantum correlations? In order to use the word correlations, we need two systems so that one will be correlated with the other. You cannot have just one system. So assume that you're having two systems, two quantum systems A and B. They're distant systems, okay, far away. For example, two atoms. And they are non-interacting, they're isolated from each other. And say that they're described by quantum state rho A and B. And assume then that these magnifying glasses represent the measurement. Assume that we measure each one, they're isolated. Now, the capital A and B are the observables that we measure, and the lowercase a and B are the outcomes of the results. So the probability of measuring these observables and getting these outcomes is given by this correlation function. Okay? And so we play with these correlations in our group. One correlation with the University of Nottingham, this man's provider. And the other Adesso to have the group. And if we take that function, we can define different classes of quantum correlations. There are four classes. I'm sure you all know entanglement. Okay? There's this one, which basically quantifies how quantum is a system, how quantum correlations. There is entanglement, steering, and non-locality. I'll talk about what that is. So this arrow basically, as you go down, it gets stronger and stronger correlations. Okay, so non-locality is the strongest form of correlation that you can use one kind. And so if we picture all the states, geometrically say, this is the following. If we take a non-local state, which is inside the cell, which is the darker one, it means that this point will be included in all the other edges. So if you have a non-local state, it belongs to the steerable, also entangled, and it's covered. It belongs to the steerable. If you take only a steerable state, which is in this state, it will not be non-local system. It will not be included in the non-local states. But it could be entangled and so on, etc. So this is the hierarchy of quantum correlations. The weakest form of quantum correlation is the short, which is the DGT, and the strongest form is non-locality. I will talk about this stuff. So in this talk, I will not talk about this word, I will talk about entanglement distribution non-locality. So, if this function, the probability of getting outcomes A and B, lowercase, by measuring observables A and B, doubles, if it cannot be expressed as this convex sum of product of probabilities, we will say that the state has entanglement, that the state is entanglement. If you're not familiar with such expressions, just think that you have two interactive systems. And here you have one probability distribution for one system, product, you can have one. Product of probability distributions means independence. So basically means that entangled states cannot be described by independent systems, even though they are not interactive. Now, this is the quantum state that describes A. Assume that we generalize this probability distribution and we substitute this with a variable number. What this means is that even though here this probability distribution is calculated on the quantum state, here we generalize it and we say, okay, let it be N. We're not assuming any Hilbert space here. This is the most general probability distribution that we can have. This, of course, is not general because it has to satisfy certain relations. Okay? So, if your state cannot be written like that, which is more general and stronger form than the previous one, we say that the state has theory. And if we generalize the other one as well, so this is independent now from the Hilbert space. Okay? Then we would say that the state is non-local, and this name comes from Bell's non-locality. Basically, this example is a hidden variable. Okay? So, an example, this maximum entangled qubit state. Okay? Here we have the qubits, 0 and 1 qubits spins. Okay? If you do the calculation, you can see that this expression calculated on this state is non-local. It cannot be expressed as that. And since it's not local, it means that it also has theory and entanglement. So as I said, this blue thing where this probability distribution is calculated on one state. And of course there will be uncertainties. But the red ones are dependent on Hilbert space, and this has consequences. Wherever there is independence from Hilbert space, corresponds to a device-independent entanglement notation. What does it mean? It means that if I have one of the systems, say I have A and you have B, isolated, non-interactive, if device-independent means the device that I use to measure this system, even if I don't know how it works, even if my device is low, even if it doesn't measure the observables that I think it measures, okay? Even still, if I get my measurement results, if I get the function of the probability, so the correlation function, if I cannot express it like this, then the state will be entangled, even though I don't know the measurement device, I don't know how it works. I don't know what I measure. I only know that by measurement, I get blue or red lights from my measurement device. For example, in order to see that it's counterintuitive, if we go to an experiment in CERN, and we touch something in the detector and we say something, people would think, if they don't know what we did, would think that we have new physics. But in this case, since the correlation of the particles are non-local, whatever you do locally, it doesn't affect the correlations. So even if you hack the measurement device, you cannot fool somebody that you say it's entanglement. And this has profound applications in quantum cryptography that we'll talk about right now. So, still, you see that only one party has independence from the Hilbert space. So we call it one-side device independence. While in non-locality, both sides are independent from the Hilbert space. So we have total device independence. And the application of that is device independent quantum cryptography, because how does quantum cryptography works? If two parts want to communicate via and use quantum cryptography, they have measurement devices, they exchange quantum systems and make the measurement. So if someone goes to the measurement device and hack it, okay, to get information, he cannot do anything because these guys can prove that the state is really happened, even though someone can hack the device and fool them. That's the point. Because anything that you do locally doesn't affect the global problem. So in the study of quantum correlations, there is an important graph here, the scalable states. If we use photons, continuous particle systems, not discrete, don't use the spin of the photon, we measure quantum electric and magnetic fields. So, one very important class of quantum states for photons are Gaussian states, like thermal states, Kogias states, Crete states. They are very, very important in the field. And they are perfectly manipulated in laboratory. And for these states, there is still a lack of measure of stability. So here you can see the strength. So I assume that we have a measure here to measure how stable the state is. This is missing for this important class of states. And also the study of the steering properties is also missing. And our work with that, which I'm not going to talk about, will be on archives with Ioannis and the Adesso provider. Would be exactly to analyze this type of correlations in Gaussian states, which I'm using in bias-independent quantum cryptography and will be very useful. So I want to do this introduction to the field and tell you a little bit about what we're doing and why it's important. I hope I made it. Okay, so I'm going to end here. Thank you very much. I hope you like the subject. Thank you.
Thank you very much for this very interesting introduction indeed to the field. We have time for one question, maybe.
Just ignore the question. What can you tell about macroscopic entanglement? There is much studies about this, how it follows your scheme.
When you say macroscopic entanglement, you mean macroscopic distances or you mean macroscopic systems? Macroscopic distances? Bodies. They have achieved entanglement of macroscopic atomic ensembles comprised of thousands of atoms. And they have also achieved entanglement for degree diamonds, okay, that were like 2 meters apart. And they have achieved quantum teleportation between diamonds and atomic ensembles as well. So this is the latest achievement that I know. And they're quite impressive.
There is also in particle physics, EPR, right? In meson factors, that's also 7 years. That's an entanglement.
No, but it's better to entangle them to 20.
Yeah.
One more question, maybe? Okay, so, oh, sorry.
Okay, I would like to know these steering states, whether they are more easy to be produced than in the non-local states. It seems it might be easier to produce a symmetric rather than an unsymmetric state.
So here, as you go down to stronger and stronger quantum correlations, it's more difficult to produce them. So at the easiest, here are the most easy to produce in entanglement states as well. But as you go down to non-cavity, it's harder and harder. So that I think answers the question.
Yes, thank you.
Okay, so thank you again.
Thank you very much.
And